For the RLC in the parallel, we have resistor, inductor, and a capacitor connected in the parallel, and then to the AC source as well. So now let's assume that the current through the source is equal to the I, okay, depending on the time t, and the potential difference across the source equal to delta V. Then the current through the resistor and the inductor and the capacitor is just equal to this. And we know that the current through the source, right, it must be equal to the current through the resistor plus the current through the inductor, and then plus the current through the capacitors. Okay, so we have this relationship. Also, the potential difference across each component, okay, so across the R, across the L, and then across the C must be equal to each other as well. So now in this case, to write down the phasor diagram, right, the common variable must be the potential difference across each component. Okay, so let me just make the horizontal axis to be the delta VR. To be the delta V. Wait. Okay. So this one for the delta V naught for the maximum amplitude, right? Delta V naught here. Okay. So let's consider the current through the resistor first. We know that the current through the resistor and the potential difference across the resistor must have the same phase, right? So in this case, it means that the current through the resistor must point to this direction, and let's say that this is equal to the IR, right? Okay, so let's consider the IL. The phase of the current through the inductor lags the phase of the potential difference across the inductor by the 90 degree. From this table, okay, from this table, we said that for the inductor, delta VL leads the current by the 90 degree, or we can say that the current lags the delta VL by the 90 degree as well. Then it means that the current through the inductor must point to this direction, so this will be the IL, okay, because the delta V naught is leading the IL by 90 degree. So now about the capacitor, again, from this table we say that delta VC lags the I by 90 degree, right? It means that the I will lead the delta VC by 90 degree. So the current through the capacitor leads the potential difference across the capacitor by the 90 degree. So it must point to this direction. This will be the I and the C. Okay, and just making the 90 degree to each other here. So now we just want to combine, okay, again, we just want to find the I naught, right? The total, the maximum current amplitude here. Then again, we need to combine the IC, the IL, and the IR as the vectors. So now for the IC and the IL, so let me just assume that the IC is greater than the IL. Then we can find this. Okay, so this one is going to be equal to the IC and then minus the IL. Okay, so now let's combine here and here. Okay, if we combine the IC minus the IL with the IR, right, then we can get this vector. So let's say that this equal to the I naught. Okay, it's just equal to the I naught. which is the maximum current amplitude, which is the maximum current amplitude of this value of the IT here. Okay, so we have the I naught, right, equal to the square root of the IR square, and then plus the IC minus the IL, and then square. Okay, so we know that IR, okay, equal to delta V naught and then over the R and square, okay, from the previous topic, plus the IC just equal to the delta V naught and then over the XC, and then minus the IL, the delta V naught, right, and then over the XL, and then square, and then totally square root. So the delta V naught is just the common variable, so we can just bring it out from the square root here. Then we have the delta V naught, right, and then the square root of the 1 over the R square plus the 1 over the XC, and then minus the 1 over the XL, and then square, and then square root. Okay, so now let's look at the unit of this term, right? So you can see that, okay, let's just consider this one. It's just the 1 over the R square and then square root. It means that the unit of this term must be equal to the 1 over the R. So the R is resistance, right, unit as ohm. So it means that we can define the impedance for sorry, let me take a look here of, okay, the impedance of the parallel circuit, right? So let's say that, let's define the 1 over C is just equal to this guy, okay, 1 over C equal to this guy, because the unit of dimension of this one, right, just the 1 over the resistance. So that's why we have the 1 over C here. So the C here just means the impedance of the parallel circuit here. Okay. It means that, okay, to find the C, right, you need to know the R, the XL, and the XC. So don't forget to flip this equation to get the C, okay? I mean, you just compute this number already. Don't forget to flip this one to get the C. Okay, and then we also find the phase difference, right? The phase difference. The phase difference between the IT, okay, which is the current through the source, and delta VT, which is the potential difference across the source here. Okay, so how can we find this? Then again, let's look at this phasor diagram, right? We have the I naught, okay, in this direction, and we have delta V naught in this direction. So it means that this angle is going to be equal to the phi. So from this angle, from this phasor diagram, you can see that the phase of the current, right, is leading the phase of the potential difference by phi from this phasor diagram. Then we have that the tan phi, okay, the tan phi equal to the opposite and then over the adjacent. The opposite equal to this one, right? It's just equal to the IC minus the IL, and then over the adjacent. Adjacent is just equal to the IR. Okay. But then when we plug in the IC equal to delta V naught over the XC, the IL just delta V naught over the XL, and the IR, right, just equal to delta V naught over the R into this equation. So delta V naught just cancel out. Then finally we can get that equal to the R, and then the 1 over the XC minus 1 over the XL, and that's it. Oops, sorry. Okay, right, this is what we get. So examples of the RLC in the parallel circuit, we give it later, okay? But now let's talk about the RLC in the mixed circuit. This one. Okay, what does it mean? It means that right now we have, okay, let's say the circuit 1, circuit 2, and then connected in the parallel to each other. Okay, circuit 1 just means the combination of the R, the L, and the C. Circuit 2 again just means the combination of the R and the L and the C. Okay, so this is called the mixed circuit. Okay, but in this case, I mean, I will give you what is inside the circuit 1 and the circuit 2. So let's just look at it as the module. Okay, actually we can have the circuit 1 and the circuit 2 connected in the series as well, but I mean for this example I just want to give only the idea if the circuit 1 and the circuit 2 connected in the parallel to each other. So now let's assume that the current through the AC source equal to the I, okay, and the potential difference across the AC source equal to delta V, and we know that the current through each circuit, right, equal to the I1 and the I2 respectively. Then we just want to find the phase difference between delta V and the I here. Okay, we just want to find the phase difference between delta V and the I. So how can we solve for that, right? Let me give you some idea first. So now for the circuit 1, okay, I mean we don't know, I mean right now we don't know what the circuit 1 is, but let's assume that we can get the phasor diagram of the circuit 1 to be like, let's say this one, okay, let's say the I1 and then the phi1, and let's say delta V1. So let's assume we know this, okay, let's assume that we can find this phasor diagram from the circuit 1. So now from this phasor diagrams, it means that the phase of the current is leading the phase of the delta V1, right, by the angle equal to the phi1. So now for the circuit 2, let's assume that okay, so let's assume that the phasor diagram that we can find to be something like this one, and the I2, and let's say that this is going to be the phi2. Okay, so now from this picture you can see that the delta V2, right, is leading the I2 by the phi2. Okay, but don't forget that, I mean, I just assume to be like this as an example, but actually it's not necessary to be like this. Okay, so let me say that we just want to find the phase difference between the current I and the potential difference delta V, right? Okay, look here, circuit 1 and circuit 2 are connected in the parallel. So now for the parallel combinations, it means that the potential difference across each circuit must be the same, right? So now I just want to make delta V as a common variable. Okay, so we know that delta V1 must be the same as delta V2 and must be the same as the maximum voltage amplitude of this delta V, right? So let's assume that it just equal to the delta V naught. Okay, so then the phasor diagram we can get that, okay, for the horizontal axis, right, we can have the delta V naught to be the horizontal axis because this is the common variables. So now for the I1, right, the I1 we just go like this, and it's just making the angle phi1 to the delta V naught. I2 is gonna go like this, right, and it's just making the let's assume that it just go like this, okay, and it's just making the angle phi2 to the delta V naught here. Okay, so now we just want to find the total current, let's say the I naught, and we just want to find the phase difference between the I and delta V. So as I mentioned before, the idea of this one is just the same as when we sum the two vectors together. Okay, so now let's break the vector I1 first. So okay, we have this one, right, and this one. Okay, so this component is with the I1 and the cosine phi1, and this component is going to be the I1 times the sine of the phi1. Okay, this will be the horizontal and the vertical components of the I1. So now for the I2, we can have this component and then this component. So this will be the I2 cosine the phi2, and this will be the I2 times the sine of the phi2, right? So now, okay, let's just combine the horizontal component together and the vertical components together. So now for the horizontal components, we can have that. Okay, so let's say the IH for the horizontal component is going to be equal to, okay, in this case, it's just equal to the I1 cosine the phi1, right, and then plus the I2 cosine the phi2. Okay, so don't forget that these two just point in the same direction, so that's why we need to add up to each other. But now for the IV, for the vertical components, right, so this is going up, point in the upward direction, and this one just point in the downward direction. So we have the I1 times the sine of the phi1 minus the I2 times the sine of the phi2, right? Okay, so then let's summarize. We have delta V naught in this direction, and then we have the IH in this direction, and let's assume that we have the IV in this direction, right? So now we need to combine this IV and the IH together. So it means that we need to compute, we need to use the Penning theorem to solve for this one. Okay, then okay, let's make this line first. Okay, this will be the I naught. Okay, it will be the current amplitude of this one already that we got, and then the angles between the I naught and delta V naught is just equal to this one, phi. Okay, equal to phi. Let me emphasize again. So the I naught here is just be the current amplitude, okay, amplitude of the IT, and the phi here it just be the phase difference, right, between the I and delta V. Delta V is just the potential difference across the source, and the I just be the current through the source here. Also, we can use the Penning theorem, right, to find the I naught, and we can use the trigonometry identity to find the phi. And we have that the I naught is just equal to the square root of the IH square, and then plus the IV square, and then the tan phi, right? Tan phi just equal to the IV and then over the IH. Okay, so that's to be the idea. But actually we can have many types of the mixed circuits. Okay, but I mean it just give you the idea how to solve for this one. So the idea is that you need to know the phasor diagram of each circuit first, right? And then you need to combine the phasor diagram together, and then you need to break the current to be the horizontal one and the vertical one, right? And then combine together using the Pregnant theorem. And then you can use the trigonometry to solve for the phase difference between the current I and delta V.